All right, so today we're going to take a look at a few more complicated uses of exponential and logarithms. Actually, mostly exponential. Logarithms you can't do much with other than use them as they are. But our exponential function can be utilized a few different ways to model certain situations. So the first that we saw already actually we'll do two. Okay, is exponential growth and decay. Right, so we know what exponential growth looks like, a general formula like that. Okay, exponential decay would be the opposite, where we fall down like that. Exponential growth is great for modeling things like population, if we're talking about cells. So in biology, I just had the name. When cells split, right? You know, you have one cell, it splits to two. Those two cells split to four. Okay, that's exponential growth. That would be something like 2 to the x. Most exponential growth formulas have the form a e to the bx. Okay, a here is our what we call our initial population. All right, so if I start off with 1,000 cells and they're doubling, okay, my equation will look like this: 1,000 times 2 to the x. All right, so x is usually our time, right? So depending on how often it splits, you know, maybe it splits once every day, right? So after 1 day, it doubles twice. So 1,000 times 2. After 2 days, it doubles twice again. So 1,000 times 4. All right, so that's how we deal with it like that. Okay, our decay is similar. All right, we have an initial population, A, but now we're raising it to the negative bx. Okay, so remember, having that negative there swaps how the graph looks. All right, and here I have two examples. All right, so say here 60 times 2 to the x. If I zoom out, that'll be better. Okay, it's an extremely steep slope. All right, we shoot up pretty quick. So I start off with a population of 60, and then, you know, maybe every hour it doubles. So after 1 hour, I can't even find it on here, I would have 120, right? After 1 hour, it doubles again, so I'd be all the way up at 240, right? So you can see how that acts, how that behaves. And that's why when you hear stuff like on the news, if something is growing exponentially, then it's growing really fast and can get out of hand before you know it. Okay, and then on the other side, we have our exponential decay. So I talked about half-life. All right, we have things like that when we're trying to use carbon dating. Okay, we can use a negative exponent or a fraction in here. Okay, so this 1/2 tells me that I'm taking half of my 100, and then x is how many times it happens. Okay, this is the same as 2 to the negative x. All right, both those graphs give me the same, or both those equations give me the same graph. All right, I don't want to spend too much time on that since we've already kind of talked about that. Our next example, this is where things start to get interesting. What I do with it, what's its name? Okay, the next is a Gaussian model. Let me give you what that looks like. So here, again, we have an exponential, but now the power involves a negative x squared. All right. So that does things with our exponential equation. We use Gaussian models a lot. They use it in statistics and probability. Okay. If you guys are aware of something called the bell curve. Okay. The bell curve is used for things like SAT scores and IQ levels. So here, okay, at the peak, that's where most of your data is held, right? So for IQ levels, that would be 100 IQ, which is you're on pace. You're at where you're supposed to be, you know, mentally. Then it falls off, okay, as you go up and as you go down, right? So most of the population is average IQ. You know, as we get higher, 200 IQ, okay, that would be very little of the population is, you know, super geniuses. And then on the other hand, having a low IQ, okay, like 50 IQ, okay, also a low population. As you move up, okay, it gets closer and closer, right? The same thing for SAT scores. If you took all the students' SAT scores like throughout the years, okay, and you plotted them kind of on a, I don't know if you guys did something like this in Algebra 2, right, where you would plot points, you would plot your data, right? Your SAT scores would kind of take that form as well. Right. So here I do have another example. So just the basic e to the negative x squared. Okay, so that we're not manipulating anything. So this is your general Gaussian equation, right? And that's what our graph looks like. We have that kind of that hump. Okay, notice it doesn't go above 1, right? If we're talking about percentages, percentages never go above 100%. If you're talking about probability, okay, it's either between 0 or 100%. And here we can see it stops at 1. 1 would be 100%. Okay, so on your IQ graphs, you know, this here, this might be 50%, right? We wouldn't reach 100% because if 100% was in a group, then it wouldn't be anywhere else. All right, so that is our Gaussian model. The last exponential type we have is called the Logistic Model. Okay, and oops, no, that's not what I want to do. Okay, and even though it has the word log in it, okay, it doesn't have to do with logarithms. Logistic has a very complicated setup. Well, not very complicated, but much more than what we're used to seeing. So here we have an exponential in the denominator with a negative exponent. Now, the reason we can't bring this up to the top is because this is tied in with this +1. Right, so all of this is on the bottom, and we can't move that to the top. So having an exponential in the denominator with a negative exponent gives us a really interesting graph. And I'm just going to show you that. Okay, that's okay. Thank you for letting me know. So here, our graph behaves very interestingly. With logistic growth models, we have two horizontal asymptotes, okay, which we never really see anywhere outside of this. Usually, one of your horizontal asymptotes is the x-axis. Well, you guys can't see that because I have the graph up. Usually, one of your asymptotes is the x-axis, right? So you would have that invisible line up there. And then depending on what numbers you have here, you have an upper limit, okay? So we have a lower and an upper limit. So what's interesting here is the way this graph behaves. Okay, up from this point, coming from the left, okay, we kind of have an exponential growth. Okay, it's increasing. We call it increasing growth. That's a little sloppy. I can't write too tiny with these markers. Okay, so it's like exponentially increasing, right? We slowly increase, and then the amount that we're increasing gets larger. So it's an increasing growth. Then, once we hit kind of like a threshold, a turning point, okay, I'm still increasing, but I'm not increasing as much as I was before. And in fact, my increasing intervals are decreasing. Okay, so we have a decreasing rate of growth over here. All right, so it's kind of exponential on this side, and then it kind of turns into almost a logarithmic one on this side. They use this, again, for population, but more specifically for something like spread of a virus. So actually, with COVID, this is how the graph should have looked as long as we took precautions. If people were doing their job and social distancing and wearing masks, this would be our infection rate, right? So at first, nobody's really infected. Obviously, nobody has the disease. It comes into contact with humans. And at first, it grows exponentially, right? Every person's given it to 2 people or 3 people. So we have an exponential growth. Then eventually, it hits its threshold, either because we start doing what we need to do, or there's medication involved, there's treatments. So it's still spreading, but that spread isn't as fast as it was before. Okay, and then eventually, it tapers out. So you still have infected people, but the number of infected people isn't really increasing anymore. Okay, we started to look like this, maybe, in the summer, right? This was last March. We started hitting this last March, April, May, and then June and July, it started to do this, and then it just started shooting up again. Now, this upper limit depends on a few things. Again, if something's introduced that it automatically decreases it. But sometimes this upper limit is the total population, right? Once everybody's infected, you can't infect any more people. You're not going to go above that limit, okay? But hopefully things come into play where that gets decreased on its own through outside sources. All right, and then finally, we have logarithmic models. We saw the graphs of those. All right, they increase, but not very fast. Okay. We do use, I might have mentioned this, we use logarithms to deal with earthquakes. Okay, the Richter scale. When there's an earthquake, they say it's a 8.0 on the Richter scale. Well, They use a very basic logarithmic equation for that. Okay, it's just the log of I over I naught, where I is what's known as the intensity. So there's a separate calculation for intensity. That involves a little physics and what's called wave energy. So, when they measure the actual waves of the shaking, right? Because everything is in waves. All right. I don't know, if you're in physics, you'll learn that. Okay. Light, sound, actual water. Okay. Everything moves in waves. So that's how we get that. We also have decibels. Okay. So for audio, decibels. Yeah, that's right. Okay, again, we have some sound intensity, and we can measure the sound using logarithms, right? So notice it's base 10, right? So what that does is that kind of fits everything on a scale from 1 to 10, right? We're not going to have an earthquake on the Richter scale over 10, otherwise the Earth would split, and it would be catastrophic. So yeah, any questions about that stuff?